As I had earlier discussed in my previous lecture, that modulation is an essential part of communication process. Presently, we are considering the propagation of audio signal. So, in the process of modulation, two important waves are there. The first is the modulating wave or the message signal, and the second is the carrier wave, which is a wave of comparatively higher frequency. So the modulating wave, we have to propagate from one point to another, and for the process of modulation we have to make use of the carrier wave. The message signal or the modulating wave is of comparatively lower frequency, and the carrier wave is of comparatively higher frequency, which lies in the radio frequency range. Presently, I will discuss amplitude modulation in some details. We know that in amplitude modulation, the amplitude of the carrier wave, this is the carrier wave and this is the message signal. In amplitude modulation, the amplitude of the carrier wave varies in accordance with the instantaneous value of the message signal. The amplitude means the highest point or the highest value in a particular wave, and instantaneous value means the value of that particular parameter at a particular instant of time. At different points of time, the instantaneous values of the parameter, whether it is voltage or current, the value of that particular parameter at a particular point of time is known as the instantaneous value. So this is the carrier wave, and the highest point is the amplitude. If we vary the amplitude of the carrier wave in accordance with the instantaneous value of message signal or modulating signal, then the resulting wave will be known as the amplitude modulated wave. Therefore, as the instantaneous value of the message signal is increasing, the amplitude accordingly increases. The amplitude, which was earlier constant, now it starts to vary in accordance with the instantaneous value of the message signal, and when it decreases, then the amplitude of the carrier wave also decreases in accordance with the instantaneous value of the message signal. So this is the final form of amplitude modulated wave. Now, in the previous slide, we have seen that the message signal or the modulating signal was represented by Vm sine omega mt, where Vm is the amplitude of the message signal or modulating signal, and the carrier wave is represented by Vc sine omega ct, where omega c is the angular frequency of carrier wave, and Vc is the amplitude of that carrier wave. Now in the process of modulation, we define a very important term which is called modulation index. Modulation index is defined as the ratio of Vm and Vc. That is, the modulation index is represented by the term M, and M is equal to the amplitude of the modulating wave divided by the amplitude of the carrier wave. This modulation index or the index of modulation is a very important factor which determines the quality of modulation, or the value or the numerical value of modulation index gives us an idea how the quality of the message which will be received at the receiver end will be it will be whether it is of good quality or it is of some lower quality, or whether it will be a distorted kind of signal. We will see in further slides how this modulation index value gives us the idea of quality of received signal. Let us see how it is capable of defining or giving an idea of quality of the signal which will be received at the receiver. The first case is if the index of modulation is less than or equal to 1. That is, if m is equal to or it is less than, suppose if we consider the case when m is smaller than 1. M is smaller than 1, it is quite obvious that if Vm, that is amplitude of modulating wave, is less than the amplitude of the carrier wave, then the value of M will be less than 1. So if this is the case, that is if M is less than 1, then this is called linear modulation or under modulation. It is quite evident that if Vm is smaller than Vc, then the amplitude of modulating signal is less than the amplitude of the carrier signal. Therefore, it can be seen from the figure that if the amplitude of the modulating signal is less than the amplitude of carrier signal, then the envelope will not reach the lowest point of this modulating signal, because it is quite evident that the amplitude is less than the amplitude of modulating signal is less than the amplitude of the carrier signal. Therefore, when it is decreasing, then it is not reaching the it's the lowest point where the amplitude of the carrier signal reaches at its lowest point. So when the envelopes of the positive side and the envelope of the negative side do not touch each other, then it means that the index of modulation is less than 1, and it is called linear modulation or under modulation. And in practical purposes, this kind of modulation, that is linear or under modulation, it is the most commonly used type of modulation. And when this kind of modulation is used, then the received signal, when we will demodulate the wave at the receiver, then the signal will be obtained in its perfect form. It will not be distorted. As in the previous slide, I have explained that the index of modulation gives us an idea about the quality of signal which we will receive at the receiving end or at the receiver. And I had also discussed that if the modulation index, that is M, is smaller than 1, then it is called the case of linear modulation or under modulation, and this is the most commonly used category of amplitude modulation. Now, as there are some other categories of modulation also, depending upon the numerical value of the index of modulation, and these cases are categorically depicted in this figure. In the first figure, this is the case of under modulation or linear modulation. As we can see, the amplitude of the message signal is smaller than the amplitude of the carrier signal. Therefore, this is the case of under modulation, as we have seen in the previous slide. This is only 50% modulation, or we can say that the numerical value of M is 0.5. That is, the amplitude of the message signal is half the amplitude of the carrier signal. So it is only 50% modulation, or the index of modulation is 0.5. The second case is, in the second figure, you can see that the lowest point of the modulating signal is touching the negative peak uh, of the envelope on the negative side. It means that the amplitude of the modulating signal is just equal to the amplitude of carrier signal. Therefore, when it is coming uh, it is coming downside, then it will touch the peak of the envelope on the negative side. Hence, it is the case of 100% modulation, or in other words, we can say that the value of index of modulation is 1, or we can also define in the present case that for 100% modulation case, or m equals to 1, the amplitude of modulating signal, that is Vm, is equal to the amplitude of the carrier signal, that is Vc. Vm is equal to Vc. This is 100% modulation. Now in the third diagram, the case is shown where the amplitude of the modulating signal is greater than the amplitude of the carrier signal. When the amplitude of the modulating signal is greater, then while it is coming down at the negative peak, it crosses over the x-axis and goes to the uh, negative side, as is clear from this figure. Since the amplitude of modulating signal is greater than that of the carrier signal, therefore it is just crossing, when it is coming down, it comes to the negative side. So the envelopes are overlapping. The positive side is going to the negative side, and the envelope of the negative side is crossing over to the positive side. Therefore, the amplitude modulation seems somewhat like this, as shown in the third figure, and this is the case of over modulation. In this case, the modulation is 150%, or the value of m is 1.5. It is greater than 1. When we are dealing with the over modulation, then the signal which will be retrieved at the receiving end, or which will be received at the receiver, that will be a distorted signal. As you will see when we will discuss demodulation process or the detection process, then this kind of signal which will be received at the receiving end, or at your radio or your transistor, that will be a distorted signal, and the quality of the signal will be greatly deteriorated. Okay, so this is the case of overmodulation. In the present diagram, the carrier wave amplitude Vc is depicted, and over that carrier wave, or over the amplitude of the carrier wave, the envelope of modulating signal or the message signal is shown. As we can see in the diagram, Vc is the amplitude of the carrier wave, and upon that carrier wave is superimposed the message signal, whose amplitude is Vm. As we can see that the amplitude of the message signal is less than the amplitude of the carrier signal. Therefore, it is a case of undermodulation or linear modulation. And the equation for the modulating signal is Vm sine omega mt, or we can say that the instantaneous value of the modulating signal at a particular instant of time is Vn sine omega mt. And A is the, as we can recall the previous discussion, that at any point of time the Carrier wave amplitude varies with the instantaneous value of the modulating signal. Therefore, we can say that at this particular instant of time where capital A is shown, this will be the amplitude of the Carrier signal at this specific time where this letter capital A is written. Normally the amplitude of Carrier wave is Vc, but when it undergoes uh, amplitude modulation, then its amplitude will change according to the instantaneous value of the message signal. Therefore, at this point, the amplitude of the modulated signal will be capital A. Now we will see in the next slide how this amplitude A will be defined in the mathematical form. As I had described in the previous slide, uh, capital A at a particular instant of time is the amplitude of the carrier wave, which depends upon the instantaneous value of the modulating signal or the message signal. Therefore, if you refer to the previous diagram, then the amplitude at a particular instant, that is A, is equal to the Carrier wave amplitude, that is Vc, plus the instantaneous value of modulating signal, which is small vm, which is depicted by small vm. Or if the value of Vm, or the instantaneous value of message signal, is substituted in this equation, and the amplitude of the modulated wave at a particular point of time will be Vc plus Vm sine omega mt. Now we know that the index of modulation is denoted by small m, and it is a ratio of Vm and Vc, or small m is equal to Vm upon Vc. Therefore, Vm can be replaced by m multiplied by Vc, or it is rearranged as Vc inside the brackets 1 plus m sine omega mt. This is the amplitude of the modulated wave. This is the amplitude. Okay, hence the equation of amplitude modulated wave is, or we can say that A is the amplitude, final amplitude of the Carrier wave, uh, whose amplitude is being varied according to the instantaneous value of the modulating signal. This is the amplitude of the modulated Carrier wave. So we can find out the equation of the amplitude modulated wave, because A is the modified amplitude. So the final equation of the amplitude modulated wave will be amplitude multiplied by sine omega ct, that is Vc into 1 plus m sine omega mt into sine omega ct. And if it is simplified, then we get it is equal to Vc sine omega ct plus m into Vc sine omega ct into sine omega mt. Now, if we further simplify this equation, so we can rearrange the second term in simple, using a simple trigonometrical transformation of the second term. So it will be, the second term will convert into mvc divided by 2 cos vc, omega c minus omega mt minus vc upon 2 cos omega c plus omega m into t. We have simply rearranged the second term into further two terms, in which the two frequencies omega c and omega m are converted into that difference and addition. Now, if we decipher or interpret this entire equation, which is the equation of amplitude modulated wave, then it is the first term. What is the first term? The first term is Vc sine omega ct, which is purely carrier wave. This is the equation of the carrier wave. So if it were the uh, a plain carrier wave, then its equation would have been Vc sine omega ct. But since we are now considering the amplitude modulated wave, so in this case, in addition to the carrier wave, two additional terms are there. The first term is contains the frequency omega c minus omega m, and the second term contains the frequency omega c plus omega m. Therefore, in the unmodulated carrier wave, two additional terms are added, and these two terms correspond to two side bands which are present in the amplitude modulated wave. The lower sideband has a frequency omega c minus omega m, where omega c and omega m are the angular frequencies. And omega, this is the lower sideband, omega c minus omega m, and the upper sideband has the angular frequency omega c plus omega m. Or we can say that if we prefer to use a simple frequency in place of angular frequency, then the lower sideband has the frequency fc minus fm, and the frequency of the upper sideband is fc plus fm. Therefore, we can say that in the pure carrier wave, the frequency was Fc. In the pure modulating wave, the frequency is Fm. But when these two waves are combined to form the amplitude modulated wave, then the additional frequencies are added to them. Hence, the entire frequency bandwidth of the amplitude modulated wave will be Fc plus Fm minus Fc minus Fm, and it is simplified as 2Fm. So 2Fm is the uh, entire bandwidth of the amplitude modulated wave, where Fm is the modulating frequency or frequency of the message signal or modulating signal. Therefore, if we consider that we have to propagate a audio signal of frequency 200 Hz, then the entire bandwidth or frequency needed will be 2 times 200, that is 400 Hz. This is the bandwidth required for the propagation of the amplitude modulated wave. As we have seen in the uh, previous slide, when a modulating signal is superimposed on the carrier signal and it is converted into amplitude modulated wave, then the entire bandwidth is 2 times the modulating frequency. So if the modulating frequency is a single one, for example, if it is 200 Hz, then the entire bandwidth will be 400 Hz. Now suppose that instead of a single frequency, if a range of frequencies is to be propagated or it is to be transmitted, then let us find out what will be the entire bandwidth required for the propagation of that range of frequencies. In this diagram, a particular example has been discussed. For example, in the present case, the carrier is 700 kilohertz, because naturally the carrier has a frequency much above the frequency of audio signal. So in this example, the carrier wave has a frequency 700 kilohertz, and the frequencies of audio signal or the modulating signal, it is from 300 Hz to 4000 hertz, because the audible signal has a audio frequency range 20 hertz to 20 kilohertz. So suppose we have to transmit the audible frequency from 300 hertz to 4000 hertz. So what happens if we calculate the upper sideband? Then upper sideband is the carrier Fc plus Fm. So Fc is 700 kilohertz. When 4000 hertz, that is the upper limit of the audible signal, is added to that, then the upper limit of the upper sideband, or the higher limit of the upper sideband, will be 700 kilohertz plus 4000 hertz. This is the upper limit of the upper sideband. And the lower limit of the audible range is 300 hertz, because we have to modulate the signal of 300 to 4000 hertz. So the lower limit of the upper sideband will be 700 kilohertz plus 300. That is, it will be 7,300,000 hertz. So the upper sideband will contain the frequencies from 7,300,000 hertz to 7,04,000. This is the upper sideband. And in the lower case, the lower sideband, if it were the single frequency, then the lower sideband is Fc minus Fm. But in the present case, instead of a single modulating frequency, we have a range of frequencies, that is 300 to 4000 hertz. So to calculate the lower sideband, we will take the carrier as 700 kilohertz. So 700 kilohertz minus 300 hertz, this is the limit of lower sideband. And then again 700 kilohertz minus 4000 hertz, and this will give us the upper limit of the lower sideband. So this is the frequency spectrum of amplitude modulated wave when a range of modulating frequencies are to be transmitted. And in the present case, we have taken the range of frequencies as 300 hertz to 4000 hertz. Now we will see what will be the entire bandwidth required for the propagation of this kind of frequency spectrum. Then we will see that in the next slide we will discuss what will be the final bandwidth required for this particular case. As we have seen in the previous slides, that if a single frequency, that is FM, is to be propagated after amplitude modulation, then it is simply 2 times FM. If 200 hertz is to be propagated, then the bandwidth required will be 2 into FM. But in the present case, we are not propagating a single frequency, but we are propagating a entire frequency range of 300 hertz to 4000 hertz. So we will see what will be the bandwidth required for the propagation of this kind of entire band of frequency. Now in the second diagram, the frequency spectrum of amplitude modulated wave for a single modulating frequency FM has been shown. In the previous diagram, we have considered the case when instead of a single modulating frequency, a range of modulating frequencies or a range of message signals was to be transmitted. But in the present case, we have a single modulating frequency FM which is to be transmitted. So the carrier frequency is Fc. The upper sideband will be Fc plus Fm, carrier frequency plus the modulating frequency, that is Fm, and the lower sideband will be Fc minus Fm. Therefore, the bandwidth, which is the difference of upper sideband and lower sideband, will be Fc plus Fm minus Fc minus Fm, that is 2 Fm. Therefore, in the present case, when a single modulating frequency has to be transmitted in the form of a modulated wave, then the total bandwidth required will be twice the modulating frequency. Now the question arises, if instead of a single modulating frequency, we have a complete range of modulating frequencies that have to be transmitted by adopting the method of amplitude modulation, then in that case, if a complete range of frequencies is to be transmitted, then in that case the bandwidth required for propagation of a range of frequencies is twice the highest frequency in the frequencies to be transmitted. Suppose if we take up the case of the previous example, in which the range of frequencies was from I think 300 hertz or 400 hertz to I think it was 4000 hertz. So the higher range or the maximum frequency to be transmitted is 4000 hertz. Then the total bandwidth required will be 2 multiplied by 4000 hertz, that is 8000 hertz or 8 kilohertz. Therefore, it is a simple calculation. If the range of frequencies is from 20 to 20,000 hertz, that is the complete audio range, then the bandwidth required will be 20,000 multiplied by 2, that is 40,000 or 40 kilohertz. So this is the simple calculation to find out the bandwidth required for propagation of amplitude modulated wave. And this diagram shows the frequency spectrum of AM wave for a single modulating frequency. Now we come to the point power relations in amplitude modulated wave. As we have seen in the previous slides, the equation of amplitude modulated wave is Vc sine omega ct plus mvc by 2 cos omega c minus omega m into t minus mvc by 2 cos omega c plus omega m into t. This is the entire range of frequencies and the complete equation of amplitude modulated wave. If we analyze this equation component wise, then the first term is the gives the idea or it represents the carrier wave. The second term represents the lower sideband, and the third term represents the upper sideband. So if we transmit only carrier wave, then this is the first term represents the carrier wave, but in the amplitude modulated wave, two additional terms are present in the equation of the amplitude modulated wave. So if we have to carry two extra terms, or if we have to carry a wave which is containing two more frequencies, and for these two frequency components we have some amplitude and some other variations also, or it is in the form of a complete wave, lower sideband wave and the upper sideband wave. So naturally, had it been only the carrier wave, then the power required will be only it was concentrated only for the carrier wave. But since two additional terms are also present in the amplitude modulated wave, so additional power has to be supplied for propagating the amplitude modulated wave in comparison to the case when only the carrier wave had to be transmitted from one place to another. And these two power terms will come along with the presence of the lower sideband and the upper sideband. And in the next slide, we will calculate how much additional power is to be added to the transmitter in order to give a momentum to this amplitude modulated wave uh, to uh, to get transmitted from the transmitter to the receptor. As we can see in the first equation shown in the present slide, the power of amplitude modulated wave will contain three terms. The first term is the power contained inside the carrier wave, because the first term in the equation of amplitude modulated wave is the carrier wave. The second term is the lower sideband. Therefore, the second term in the power equation will be power contained inside the lower sideband. And the third term is the upper sideband. Therefore, the third term will be the power associated with the upper sideband. So we have to calculate power which is required to carry these three components of amplitude modulated wave. Naturally, the power will be V squared divided by R, where R is the resistance and V is the amplitude of the carrier. Okay, or sorry, it is not the amplitude, it is the uh, RMS value. This is the RMS value of the carrier. The voltages shown are the RMS values. यहाँ पर जो VLSB and VUSB are, these are the RMS values of the different components. So the power, and we know that the RMS value of a particular wave is V divided by root 2. Therefore, the power contained inside the carrier is VC divided by root 2 whole square divided by R, that is VC square divided by 2R. Now, if we calculate the lower sideband and upper sideband powers, then we have to calculate the RMS value of these two components. In the RMS value, we take the amplitude divided by root 2, and we know that if we refer to the equation of amplitude modulated wave, then we can see that the amplitude of the lower sideband as well as the upper sideband is MVC divided by 2. You have to refer to the previous equation of amplitude modulated wave. So MVC divided by 2, this is the amplitude divided by under root 2 for RMS value whole square divided by R. So if we calculate this term, then it will be M square VC square divided by 8R. Hence the complete power equation will be amplitude modulated waves power will be Vc square by 2R for carrier power, M square Vc square by 8R, this is for lower sideband. The same power is associated with the upper sideband, that is M square Vc square by 8R. If we calculate it or if we simplify it, then it is Vc square by 2R into 1 plus M square by 2, where M is the index of modulation. Vc square divided by 2R is the power needed to transmit carrier only. If it had been only the carrier wave, then the power required would have been P carrier. So it is P carrier into 1 plus M square by 2, where M is the modulation index. Now the maximum value of M is 100%, because if we take M greater than 1, then it will cause distortion in the wave. So the maximum value allowed for the propagation of signal in amplitude modulation is M equal to 1. So in that case, the maximum power needed to propagate amplitude modulated wave will be 1.5 multiplied by P carrier. This is the power needed for carrier wave. So we can say that the power required for propagation of amplitude modulated wave is 1.5 times the power required to transmit only carrier wave. Now in the present slide, the time domain representation of amplitude modulated wave has been depicted. Vc is, this is the horizontal line in which the maximum value is constant, that is Vc. It represents the envelope of the carrier wave. If it is pure carrier wave, then the amplitude can be represented by a single horizontal line, that is Vc. Now in the amplitude modulation, we superimpose the modulating wave on the carrier wave. That is, the amplitude of the carrier wave starts to vary according to the instantaneous value of the modulating signal. Therefore, if the modulating signal has zero value, then the amplitude of Vc will remain the same, that is Vc. Now it has started increasing. The instantaneous value of modulating signal has started increasing, and in accordance, the amplitude of carrier signal also gets increased. Therefore, the envelope of modulating signal is superimposed on the carrier wave, or we can say that the envelope of the carrier wave is represented as the replica of the this modulating signal. So this is the final time domain representation of the amplitude modulated wave. Now we can see that V maximum is the maximum amplitude or the maximum value, instantaneous value of the amplitude modulated wave, and several terms are represented here. From this figure we can say that V maximum is shown and V minimum is the minimum value. V maximum is the maximum value of amplitude modulated wave, and V minimum is the minimum value of amplitude of amplitude modulated wave. From the figure we can see that V maximum minus V minimum, V maximum minus V minimum is equal to 2 times Vm. What is Vm? Vm is the amplitude of the modulating signal. V maximum is the maximum value of amplitude modulated wave. V minimum is the minimum value of amplitude modulated wave, and Vm, as we know, is the amplitude of simple modulating signal. Okay, so from this figure we can make out that V maximum minus V minimum is 2 times Vm, or Vm is equal to V maximum minus V minimum divided by 2. This is equation number 1. And what is Vc? Vc is the amplitude of the carrier wave. Okay, so Vc, if Vc is the amplitude of the carrier wave, then we can see from this figure that Vc is equal to V maximum minus Vm. V maximum minus Vm is equal to Vc, that is amplitude of the carrier wave. Now in this equation, if we replace Vm by its value from equation number 1, then Vc, that is the amplitude of carrier wave, will be V maximum minus V minimum divided by 2, and if it is simplified, then it gives us the value V maximum plus V minimum divided by 2. So if we want to calculate the modulation index, then it is M equal to Vm upon Vc. We have got the value of Vm as V maximum minus V minimum by 2, and Vc we have calculated as V maximum minus V minimum by 2. Therefore, the index of modulation can be given as V maximum minus V minimum divided by V maximum plus V minimum. So this is another representation of index of modulation.